Welcome to our channel, and today we are going to help you understand the paper encoder-based domain tuning for fast personalization of text-to-image models. The current paper introduces an innovative text-to-image personalization method that outperforms previous approaches by addressing significant shortcomings such as lengthy training times, high storage requirements, and loss of identity. By proposing an encoder-based domain tuning approach, the current paper enhances the application of personalized concepts. This is accomplished via two main components: an encoder capable of translating a single image of a concept into a word embedding, and regularized weight offsets that allow the text-to-image model to assimilate new concepts effectively. The proposed method enables rapid integration of novel concepts with minimal training steps, reducing the personalization process from tens of minutes to mere seconds, while maintaining quality. Such efficiency is not evident in the previous papers summarized, including Paper 2104.02699, which developed Restyle, a more accurate encoder-based solution for inverting images into latent GAN codes, but did not focus on personalization or rapid integration of new concepts. Paper 2211.1324, where large-scale diffusion-based generative models were introduced for text-conditioned high-resolution image synthesis, although had limitations in efficient personalization and concept integration. Paper 2002.07948, discussing personalized federated learning to adapt shared models to local datasets quickly, again not focused on the specific challenge of text-image personalization. Paper 70.1196, which improved GANs by growing generator and discriminator progressively to enhance image quality and variation, but without addressing the rapid personalization aspects. Their methods, while state-of-the-art in their respective domains, are distinct from the quick and efficient personalization through domain tuning presented in the current paper. The paper presents an encoder-based method for quickly personalizing text-to-image models, enabling them to learn and generate images of new concepts with natural language prompts in seconds rather than in long periods of time. Text-to-image personalization trains pre-existing diffusion models to understand new user-provided concepts, but existing methods are slow and have high storage demands. The authors propose an encoder-based domain tuning approach to address these issues. This involves an encoder that takes a single image of a concept, like a specific face, from a domain and maps it to a word embedding. It also includes a set of regularized weight offsets for the text-to-image model that learns to integrate additional concepts. The process relies on underfitting on a large set of concepts from a domain, which improves the model's ability to quickly learn novel concepts from that domain. With this method, a model can be personalized using just one image and as few as 5 training steps, significantly shortening the process from dozens of minutes to mere seconds without compromising on quality. The authors plan to share the code and trained encoders on their project page. The paper suggests that this method simplifies the scaling of personalization in large-scale text-to-image models, making it more efficient and accessible. This could revolutionize content creation by allowing users to easily incorporate new concepts and styles into images using just simple text prompts. Note, the given text mentions that the work was done during an internship at NVIDIA. The text discusses a new method for teaching pre-trained text-to-image diffusion models to synthesize personalized images based on specific concepts. This method is inspired by meta-learning and focuses on generalizing learning to restrict the model's degrees of freedom. The approach involves two key components: a restricted set of tunable weights and an efficient way to invert a large number of concepts. Instead of directly adjusting weights, the method uses a constant followed by fully connected layers to create model weight offsets, promoting smoothness and limiting the complexity of the learned changes. An encoder network is also used to map concept images to word embeddings. The method allows for quick training, about 11 seconds on an NVIDIA A100 GPU, and can be fine-tuned on a single image of a new concept. This approach has 3 main advantages: a strong initial setup for both the model and embedding, the ability to correct errors during the iterative denoising process, and the provision of a domain prior to identifying concepts from just one image. It significantly speeds up the personalization process, making it up to 140 times faster than previous methods. The approach is compared with other personalization techniques, demonstrating its efficiency in creating appealing results with minimal images and tuning time. The text also reviews related works, including GANs and their difficulties, autoregressive models treating images as word sequences, and advancements in diffusion models that have shown great potential in diverse and high-fidelity image generation. Additionally, it touches on image inversion techniques for reconstructing images from latent codes and the application of personalization methods in various fields, such as computer vision and recommender systems. This text discusses an approach to quickly and efficiently personalize text-to-image models without the need for storing large model data. The proposed method involves domain tuning, where the model is trained to effectively personalize to new concepts within a specific domain. This is achieved by training an encoder for effective inversion of concepts into a diffusion model, alongside weight offsets that allow the model to quickly adapt to new concepts. The encoder inverts new concepts into an editable region of the word embedding space, even if this means compromising some accuracy. By doing this, they strive to keep a balance between the ability to accurately reconstruct the input image while also keeping the model's capacity for editability and personalization. The encoder is designed using a pre-trained OpenClip V8-14 model and involves feature refinement blocks. It uses iterative refinement to predict an initial latent code from an input image and then refines this prediction across multiple iterations to improve the resultant image quality. Furthermore, to enable personalization without affecting the whole generator's domain, the text outlines an approach for selecting which weights of the model should be adjusted. By analyzing pre-existing models, the authors can determine which weights change most during tuning and thus affect personalization. This subset of weights can then be isolated for adjustment when personalizing the model to a new concept. Finally, the text describes how the diffusion model's structure is advantageous for this approach and provides an overview of the encoder architecture and the iterative refinement process. The provided text appears to describe a method for adapting pre-trained diffusion models to handle new concepts with a focus on text-to-image generation. The authors propose a twofold training approach, a word-embedding encoder and learned weight offsets. The encoder is designed to predict a new code within the diffusion model's embedding space that best represents the input concept. Weight offsets are introduced to specialize the text-to-image model for a specific domain, such as images of cats. The weight offsets are learned constants, and their optimization is regularized through a neural network. The training process involves modifying 3 attention projection matrices with cross-attention and self-attention layers identified as particularly crucial, and thus the focus of the training. The authors use pre-training over large image datasets pertinent to the target domain, employing both regularization loss and diffusion denoising loss. The loss functions help with the generalization and effectiveness of the method by introducing learned offsets to the attention weights in the model and utilizing a ranking-based modification approach. The method aims to enhance the model's ability to create images that align with the desired concepts without overfitting. In summary, the method outlined in the text is centered around enhancing pre-trained diffusion models' capabilities in generating images from text descriptions, particularly by adjusting model weights related to attention mechanisms and using specialized training techniques. The text discusses an approach for rapid personalization of text-to-image models, specifically employing encoder for tuning, E4T, which involves an encoder and weight offsets pre-trained to efficiently fine-tune the models with a single image. The process benefits from using large batch sizes to ensure good adaptation across various noise levels. The base model used is Stable Diffusion, trained on a single A100 GPU with specific training steps and learning rates depending on the domain, face, cat, art. During fine-tuning, the model is adjusted with different learning rates and number of iterations based on the domain. The effectiveness of E4T is compared to 2 previous personalization methods, textual inversion and dream booth, showing competitive or better results. Quantitative evaluation includes an identity preservation test, using a single image per identity, where E4T demonstrates good performance with high identity preservation and prompt adherence at a reduced training time. Training times for E4T are significantly less than the other methods shown, and an ablation study indicates the importance of design choices in achieving high-fidelity results. Fine-tuning step, iterative refinement, and embedding regularization are crucial for preventing overfitting and ensuring the generation of images that maintain high concept similarity and editability. The text seems to be an excerpt discussing various methods of image personalization using machine learning techniques, with a focus on a method developed by Renan Gal, Moa Barar, Yuval Atzmon, Amit H. Bermeno, Gal Chechik, and Daniel Cohen-Orr. Their method, referred to as E4T hours, is compared against other methods like stable diffusion, textual inversion, and dream booth. With both one image and 5 images personalizations, the authors claim that their method achieves comparable or better quality with just a single image and requires less time compared to other methods. They note that removing components of their method can reduce the preservation of the image's identity, and that omitting the iterative refinement module decreases the model's ability to modify the concept. This iterative refinement module appears to allow the model to focus on different aspects of the target concept at each synthesis step. The team's method also includes an analysis of the refinement process itself. By employing their concept-tuned encoder and model pair, they can observe which parts of the image are given more focus by the network during the denoising stages. This is demonstrated by freezing the encoder's predictions at a particular point and observing the effects at various stages. Overall, the text highlights advancements in image personalization with AI, emphasizing the effectiveness of the author's method in both quality and efficiency. The text discusses an approach for fast personalization of text-to-image models through encoder-based domain tuning. The proposed method excels in generating personalized images with a single input example and maintains a balance between identity preservation and editability, even when compared to few-shot personalization approaches that use multiple images. In comparisons, the author's method, green in Figure 4a, outperforms existing methods and possesses efficient personalization capabilities. An ablation study, Figure 4b, showcases the importance of various components of the method. The full method is capable of personalizing images while retaining the identity of the subject and allowing for further edits. The method is also versatile, demonstrated through its application to various domains, including abstract concepts like artistic styles, Figure 5. However, the text acknowledges limitations, noting that the approach relies on encoders trained on large datasets representing a general target class. Therefore, it's most effective for classes where such datasets exist, like faces and artistic styles. It might struggle with personalizing images of rare or unique items. Another limitation is the necessity of inference time tuning, which can burden synthesis times and requires a capable machine with sufficient memory. The encoder and text-to-image models must be fine-tuned together, making this process more memory-intensive than direct fine-tuning methods. Overall, the proposed method appears to be efficient and effective for quickly personalizing images to a specified class or style with just one or a few examples, but may have practical limitations in terms of resource requirements and the scope of applicable personalization domains. This text discusses a research paper involving a technique to quickly personalize text-to-image models using an encoder-based domain tuning method. The authors explain how large, domain-specific datasets help in establishing a good starting point for the model, which allows it to adapt better to new samples from the same domain. This concept is inspired by meta-learning methods. The authors highlight that their model can capture general outlines like face shape and accessories in early denoising steps, and later refines the details and semantics of the image, such as differentiating between a military hat and a generic one. Their approach accelerates the personalization process while maintaining high quality, as shown in their experiments. The paper also presents a graph showing the relationship between the predicted embeddings and the real-word domain embeddings during different steps of the denoising process. Iterative refinement keeps the embeddings close to the real-word domain initially, but as unique, domain-specific details become important, the distance increases. Without regularization, the embeddings can diverge significantly, resulting in overfitting and poor editability. The paper concludes that their method is effective for personalizing images within nearby domains, but has limitations when the target domain is too far from the training domain. For instance, a model trained on cats can personalize dog images, but it requires more fine-tuning to work on widely varying domains. Future work will focus on improving the encoder-based personalization and the use of hypernetworks with proper regularization to achieve instant, training-free personalization. Examples provided illustrate how this method performs when generating personalized images in various artistic styles, but it has limitations in out-of-domain personalization, which they intend to address moving forward. The provided text discusses various ethical concerns associated with text-to-image models. These models can generate misleading content or disinformation, particularly when personalized using single images, potentially creating convincing fake images of private individuals. There is a risk of inheriting and perpetuating biases from training data, but personalization can also help reduce such biases, according to research by Gal et al., 2022. Another concern is the potential misuse of learning artistic styles, which could lead to copyright infringement. However, Sean et al. 2023 have shown that technologies can protect artwork from being copied by generators, indicating a direction for future research to mitigate copyright risks. The acknowledgement section credits various foundations and grants for supporting the work, followed by a list of references, which includes various studies and papers related to text-to-image models, generative adversarial networks, GANs, image synthesis, personalization techniques, and machine learning concepts such as model-agnostic meta-learning and federated learning. The references provide a background for understanding the development and implications of techniques used in encoder-based domain tuning and the fast personalization of text-to-image models. The text appears to be a fragment from a research paper or article concerning image synthesis, specifically the creation of personalized synthesis results. Various images have been synthesized using a method described by the authors, Rainon Gal, Moab Arar, Yuval Atzmon, Amit H. Bermano, Gal Chechek, and Daniel Cohen-Orr. The listed items indicate different themes or contexts in which a subject, denoted by S. Star, has been depicted. These depictions include a range of artistic styles and settings, such as a Greek sculpture, latte art, a fighter jet pilot, fauvism, cave murals, cubism, Banksy style, street art, a Funko Pop figure, a knight in armor, a character in the style of the animated show Archer, graffiti, an Andy Warhol-esque work, comic book art, watercolor, the subject as the iconic character Ziggy Stardust, a sand sculpture wearing a Santa hat and as a wizard. Figure 9 is referenced, which likely showcases examples of the personalized synthesis results achieved with the author's method. The summarized process involves using a single input image to generate various stylized output images.